All right, so now we're going to talk a little bit about how this scoring works, right? We've already seen the VAMP score CV function, which does a cross-validated VAMP score, and now I'm going to try to give you a little bit of an intuition of how the VAMP score works and how you can imagine that the score is evaluated, right? Just to give you some intuition. Yeah, some of the figures here are thanks to Fabian Paul, a former colleague of ours, so credits go to him as well. And first, let's re-establish how a Markov state model works, because this is all somehow related. Yeah, so there is a unifying theory of Markov state models, VAMP, TICA, VAMP nets, and even more methods from fluid dynamics. And we'll see that tomorrow in more detail, but for now, let's just recap a little bit the theory of MSM. So what is an MSM? We have a set of discrete states as I. Yeah, this is what we get out of our clustering. And then what we're looking at are these conditional transition probabilities. So under elect time tau, state st plus tau is j given state st is I. This is Pij. This is our transition matrix. Or in terms of a protein, say, whether something unfolds or a helix forms, right? There can be like these state transitions. All right. And how do we start estimating one of these? We start estimating these by looking at our MD data, featurizing it somehow, and then we group together the related frames into clusters. Yeah. This is basically what k-means does for us. So first of all, we would featureize data, then we will project it maybe into a lower dimensional space. And if we do the projection right, then this will already maximize the time correlations, right? Like in the case of TICA. And then we can cluster in the space and group them together into microstates and then get our discrete trajectories out of it. Okay, so how does this look like? So if we have this helix, right, this could be microstate 1, then we have 1, 1, helix, helix, something else, 2, like partially unfolded, 3, 3, 2, 3, and then we kind of count the transitions. And then there are different ways of estimating our transition probability matrix. So we can naively, in the non-reversible case, right, where we don't enforce reversibility, we can just normalize the count matrix. Or we can have a maximum likelihood estimator, which also takes a different prior into account, right, which enforces reversibility. Okay, and then once we have that, we can have a spectral analysis of our transition matrix. Yeah, so this image you've now seen a couple times, where the large eigenvalues correspond to slow processes and the small eigenvalues correspond to fast processes. And if we did everything right, then we probably have something like a spectral gap here, like between process 4 and 5. And then we know, okay, everything below 5 or starting with 5 is probably too fast than what we care about, and we can drastically reduce the complexity of our system by going from 12 states to 4. Yeah, or to 4 processes. In this case, these 4 processes correspond to the 4 energy wells, which, you know, are connected by these 3 barriers. Yeah. And then together with these eigenvalues, we have eigenfunctions, and we can have a look at what the eigenfunctions do. We have the eigenfunction corresponding to eigenvalue 1. This one is always present. and it always does nothing. Yeah, so it's not very interesting. And then the ones after the one that is exactly 1 are the ones that have physical or chemical or some relevance, and these signify what kind of process is happening. So here we can see like this psi2, which would correspond to a jump between the left 2 states and the right 2 states. So crossing the big barrier. And then we have psi3 and 4, which are the 2 smaller barriers. Okay, and then furthermore, we can also see that these flat regions here, they correspond to more or less metastable states. So what you can say is that this psi2 corresponding to the eigenvalue lambda 2 has a certain time scale, and under this time scale we have a flat region, and this flat region under this time scale is a metastable state. And then we have a metastable state here, and we have a metastable state here and there and here and there, roughly. Okay, but as I already hinted, there's kind of a bigger theoretical framework in the background that is going on. So if we look at this expression, which is just the normalization of the count matrix, we can also write this in matrix notation and then write it down as an eigenvalue problem. So the transition matrix under the lag time tau times some vector is equal to lambda times some vector. If we insert this matrix notation here, we can just reformulate it. And this thing on the right-hand side is exactly what TICA solves for you. So what you get here is kind of a connection between how Markov state models work with TICA. One operates in discrete state space and the other operates in continuous state space, if you like. And now the rows and columns of the C, the count matrix, no longer refer to counts, but rather to features that come out of your featureizer. And the C's are no longer count matrices because you cannot count in continuous space, but they are correlation matrices. And with this, I want to introduce first the VAC and then the VAMP. So the VAC came before the VAMP and is slightly less general than VAMP. And well, so let's take it bottom up, so to say. And the idea of the VAC is that we can look at the autocorrelation function under a lag time tau of some observable psi, and then we propagate this with our T, with our transition matrix. So there is an underlying propagator that drives the system from one time step to the next. And what one can show is that this expression is bounded from above. And the closer we get to this lambda hat, the better, basically. So this is where the variational principle comes from. It's a variational approach for conformational dynamics. So that means we have an upper bound, right? Like a number, and the closer we get to that number, the better in terms of getting closer to the true propagator in our projection and our approximation, our estimates are. And what we can see here is that the maximum of this expression is achieved if psi is an eigenfunction of t. And we can see this a bit more clearly if we expand psi in an orthonormal eigenbasis of T. Yeah? So here again, we do something with the spectrum. And we get these coefficients Ci and eigenfunctions phi I. Yeah? And then under this reweighted scalar product, yeah, I didn't explain this. So this is a reweighted scalar product. Pi is the stationary distribution, and then you have the ordinary Euclidean scalar product, where each component is reweighted by the corresponding entry in pi. And then we can rewrite this. Yeah, so this is just a rewritten expression of this expression up here. Yeah? So we have the difference between psi t psi under the scalar product minus lambda hat psi psi. Okay, of psi psi we know it is greater or equal 0. And here, if we assume that it is an eigenfunction of t, we can insert lambda I psi, right? Or lambda psi. And then what we get, if we evaluate this, is just the sum. So we have the sum over all components, and then the coefficient squared times the difference between lambda I and lambda hat. And we can already see if all but one lambda is 0, which would be the case if it is one eigenfunction. And then we are already having the eigenfunction that corresponds to the slowest process. Yeah, so this is the max. Then this becomes 0. Yeah, if we have the true operator here. And we can optimize for multiple eigenfunctions by just replacing this guy, this one value, with the sum over the eigenvalues of the true operator, which we don't have in practice, right? We don't know that true operator, otherwise we would be done already. But what we know is that we can try to maximize the eigenvalue in order to get closer to the true operator, because there's always this upper bound, right? We cannot overestimate the sum of eigenvalues, but we can only underestimate them.
Excuse me?
Yes.
That upper bound is only holding in equilibrium, right?
Yes, this is for VAC. So you only have reversible dynamics. Only for reversible dynamics this holds. If you have non-reversible dynamics, then this doesn't work, and I'll explain in a second why. Okay, so let's try to give you a little bit of an intuition. This very nice example also goes back to our colleague Fabian. So let's say we have some kind of battery, right, with charged particles left and right. And we want to look at two test functions, and we want to score these two test functions. Now, what does the VAC score do? We have this state of the system, yeah? And here we have a perfect separation between left and right, or negative and positive, and here we have something awful, right? This is not a good test function. And then we propagate our system with our favorite MD integrator, yeah? And then these are the previous positions, and now these are the new positions. Yeah? And then we evaluate our test function again. So we have two states. We have x initial and x final down here. And then we put that into our test function, which is just an indicator, right? It will just tell us I am inside the left or right, or top or bottom. And then we can look at the correlation of these. So this down here in the denominator is just a constant, a normalization constant. This is just chi evaluated on x initial minus the mean value of chi norm squared. So this is constant with respect to propagation in time. This part is more interesting because this is the correlation between x, or chi, sorry, of x initial and chi of x final. And how well does it correlate? This is the question that you have to ask yourself. How well does it correlate in time after propagation? And if we have a good test function, one that separates the slow modes, then this will correlate very well. Most of the particles still are in their region, not much has changed, and this expression will be near maximal. And for the bad test function, we obtain a worse mixture, and we will get a subsequently lower score. So this is more or less how you can envision the VAC score. Yeah, does that make sense to you? Okay, so what we look for is maximizing correlation in time. And then we can go even a step further, right? Then we have the score, and the score has one very nice property, that it is differentiable. So that means we can get a gradient and suddenly throw off-the-shelf optimization algorithms at it, like Adam or gradient descent, to maximize the score. And this is exactly what, for instance, VAMP nets do. This is exactly what we will hear tomorrow. So where you just put a neural network. A neural network is a very fancy word for a function with a lot of parameters, and then you adjust the parameters with gradient descent, or a derivative of gradient descent. And this is exactly what happens in VAMP nets. So you take the score and try to maximize it. All right, so this was reversible dynamics. So why does this work in reversible dynamics? It works in reversible dynamics because if we look here, it means that the forward is just as probable as the backward. That means that the probability jump from st plus tau equals j and st equals I is the same as vice versa. Now we can rewrite this in terms of conditional probabilities. So given we start in state I and we go to state j times equilibrium probability, this is the same as starting in j going to I times equilibrium probability of j. Or in other words, pi I tij equals pi j tji. So now we have again this funny scalar product that is reweighted with respect to the stationary distribution, and under the scalar product, Tij is a symmetric matrix. And then linear algebra tells us with a symmetric matrix, we get real eigenvalues and eigenvectors. And if we have real eigenvalues and eigenvectors, then, let me go back here, this expression at the top makes sense. This only makes sense if the eigenvalue is real. If it is complex, then we don't have an order, right? We cannot really order complex numbers. Okay, so this is why it works under reversible dynamics and fails under non-reversible dynamics. Again, if I've got Rk, right, which is the sum over the eigenvalues of the true operator, then suddenly the transition matrix isn't symmetric anymore under our reweighted scalar product, and in general we get complex eigenvalues and eigenvectors. So our autocorrelation function in general cannot be bounded like this anymore. Okay, and then we can try to think of a way how to fix this. What can we do? And what we can do is called VAMP. So VAMP stands for Variation Approach to Markov Processes, and Hao and Frank did a very clever thing. They thought not only about the forward transition matrix, but also about the backward transition matrix. So you look at the backward propagator, I should say. It's not really a transition matrix, it's rather a propagator in time. So you look at the forward propagation and the backward propagation. You propagate stuff backwards in time. This is what this expression should say. So we have Cn inverse times C minus tau, and C minus tau is just the autocorrelation xt minus tau xt. So this is kind of the inverse forward autocorrelation that autocorrelates the time lagged with the instantaneous, right? And in Tika, it would be vice versa. There you would autocorrelate the instantaneous with the time lagged. And then we haveCijn, which is just the autocorrelation matrix of the time lagged data. No? And then to make things symmetric again, we don't look at the forward propagator anymore, but we look at the forward backward, which is just the ordinary transition matrix or ordinary propagator times the backward. And you can even show that this is always a symmetric matrix. Forward, backward, and also backward, forward. That doesn't really matter. So this is especially a symmetric matrix without a reweighted scalar product. So this is really, in the standard basis, a symmetric matrix. And this means that our eigenvalues and eigenvectors are real, and then with the same principle as for the VAC, we can derive a variational score, a variational principle. So again, we have an upper bound, and the closer we get to the upper bound, the closer we get to the true operator. And the expression looks something like this. Here we have the instantaneous covariance matrix of instantaneous data, and then we do a inverse square root. So this is somewhat related to a whitening operation. And then we have an autocorrelation matrix here in the middle, and then we have again such an inverse square root matrix for the time-lagged data. And this expression is also bounded from above by some constant. We don't know the constant, but we know that if we maximize this expression, we will get closer to the constant and get closer to the true operator. Okay. So this works, but this is also very prone to overfitting. What is overfitting? Take 10 points and you want to fit a polynomial to it. If you fit a polynomial to 10 points, you can think about what degree you take. If these 10 points are by chance aligned in a line, then degree 1 would be appropriate. But if we take a polynomial of degree 8 or so, then we get a very wiggly line, which probably doesn't generalize well. And this is exactly the idea of cross-validation. That means that you would take one or more points out of the estimation set, do your estimation, and then see how well the estimation captures the ones that you didn't consider for fitting the model. This is what cross-validation does for you. And one particular kind of cross-validation is called k-fold, where you would split data into training and validation sets or training and test sets. I call it training validation. The picture says training and test. And you split it into k disjoint sets and k minus 1 of these sets. So in this case, 3. This is a 4-fold. 3 sets are used for training, and the holdout, this one set, is used for testing. And then you just cycle through this. So you use this for testing, then you kind of throw everything away and start from 0 and take the non-opaque for training and then the rest for testing. And then you iterate through this, and then you get a confidence or standard deviation to your score and can know something about how reliable it is. So there's one thing that we have to take care of in terms of time series, which is that we can't just shuffle our data, right? Because the order is important. So we need to take care that our chunks are large enough so that the most of the correlation is already decayed. So what we don't want is a correlated training and test data. As soon as it's correlated, we don't have a good test anymore. In a perfect world, they would be IID.
I have a question.
Yeah.
About the training data. I don't know if you've explained and I didn't understand, but I didn't understand. But is there a way to know how much data you need to put into the training test and in the validation training set?
So in general, there is sometimes talk about the 80-20 split, which is kind of a fairly popular way of splitting your data. So you take 80% for training and 20% for testing. With time series, that's a bit more difficult because there is correlation, right? This is kind of the one thing that offsets all these methods to PCA. Because we look at the autocorrelations. And autocorrelations are bad for cross-validation because then you get also correlations between test data and training data. And to minimize this, you have to kind of select these chunks big enough that you don't have a lot of leakage of these autocorrelations into the training set, or vice versa.
Okay.
And this is depending on the lag time.
Okay. And is there a way to check if you are overfitting while doing VAMP score?
Yeah, this is exactly what this should do, right? So what you get here is you get a training score based on the train set, and you get a test score based on the test set. And they should agree,
Okay.
yeah, in a perfect world.
Oh, yeah, okay.
Okay, and this is exactly what this function does, this magic function that you've used yesterday, the VAMP score CV. This will do this. Okay, so what can we do this for? We can use this for, we can, for instance, decide what kind of features we want to consider, right? Whether we want contacts or dihedrals, distances, chemical intuition, or some approximations, sidechain flips. So we can basically make a quantitative decision on what features suit our system best. And this has also been done for, in this case, NTL9, right, where a colleague of ours looked at a bunch of features and then scored them. So here you can see we have aligned XYZ, so which is just the coordinates. Then we have residue distances, min distances, which means distances with a cutoff. Yeah, so 4 angstrom, 5 angstrom, and so on. Then we have inverse distances, log distances, E of minus distances, torsions, surface exable solution, solvent area. And we can all score these and then look at how well they perform for our data and for our operator. And you can see that, for instance, the distances here seem to work best. All right, and you can also use it for something else. So this goes a bit to, takes a bit away of what we have in mind for tomorrow. So this is the so-called Bickley jet. The Bickley jet is a two-dimensional ordinary differential equation which describes an atmospheric flow of particles. So each of these particles gets propagated by an ODE, and I've got a small video for you. So let's see if I can you see this? I hope so. So this would be the initial configuration, and I've colored the particles according to the x-axis, and then you can propagate them, and this is more or less how these atmospheric flows look like. This is the Bickley jet. And now this looks a bit chaotic, right? You can't see much structure in here, and what you can try to do is you can also try to find slow processes here. You can find slow processes based on the particle data. So you pick one particle and you evolve it with the ordinary differential equation. And this is one x0 and x tau, just one particle. And you do that with many, many copies. And then you can ask yourself, what are slow modes in here? And if we do that, then we can detect coherent sets, which can look like this. So this is something that also comes out of VAMP, where you optimize the singular functions, or the singular functions with the neural network to maximize the VAMP score. And then suddenly you can see structure in here. This is also something that you can do with it, which is not very related to molecular dynamics, I'll admit, but nice to look at. Okay, so summing up, we have the VAC and the VAMP, and with both of these scores, we can basically evaluate how good our approximation is with respect to the true dynamics. One of them works for equilibrium settings and one for off-equilibrium settings. And we can also use VAMP as well as VAC for gradient-based methods. Questions?